core shell structure with amphiphilic block copolymer. So this, I call this organization. So small angle scattering will answer some of these questions. So structural studies included means the size, the shape. We will have access to the molecular weight of the system also. We will get in trouble due to the polydispersity generally. And some molecules are anisotropic. Sometimes if you stretch a sample, for example, polymer, you will have some anisotropy due to the fact that the direction of the molecule along the stretching direction is not the same as the direction perpendicular to the stretching direction. And as mentioned above, there are some organization. You may have some order parameter and some alignment to do to different purpose. So neutrons are X-ray and X-ray have the same characteristic. Sometimes we use them as a wave, and sometimes we use them as the particles. I will not be able to explain this duality, but we use them. There are some differences. Neutrons interact with nuclei, whereas X-ray interact with the electronic shell, with the electrons. So these are the main difference between neutrons interaction with materials and X-ray. So in this way, neutrons see all elements, including very light elements as hydrogen and carbon, whereas X-ray mainly see electrons. They are able to see I, Z component, but not hydrogen and carbon. So X-ray for pure polymeric system, mainly composed of carbon and hydrogen, are not so good as neutron scattering. Since neutrons are neutral, they can penetrate inside the material over a long distance. So we will have properties of a sample, the volume of the sample. Due to the charge of the X-ray, their absorption due to the slowing down when they enter the material, and there is a huge absorption of X-ray, of photons. And the typical sample that you can study with X-ray, for soft matter especially, is of the order of millimeter. So it has weak energy, and it could be different. Neutrons has weak energy. It could be different from X-ray, especially if you go to synchrotron radiation. The energy is larger, and the flux of synchrotron radiation is much higher than the neutron. So this can damage your sample. But they have high flux, so this can be interesting also to have high flux, because neutrons, there is low flux, they are produced in the reactor, and the flux is several orders of magnitudes less than with normal X-ray lab, and especially even worse if you compare to synchrotron radiation. Neutrons has a low resolution, and whereas X-ray has a very high resolution. And neutrons possess also a spin that is not much used in case of soft matter, but it sees also all magnetic arrangement of the system, which is very hard to see with X-ray. Also, the energy of neutrons is comparable to the energy of materials. So with neutrons, we can see diffusion of molecules, movement of molecules, and Tom McLeish speak about neutron spin echo and quasi-elastic neutron scattering. This is due to the fact that the energy involved in this diffusion movement are of the order of magnitude of the energy of neutrons that are sent to the sample. So some principle. So I start at the beginning. So neutron and X-ray are considered as a wave. When they come to the sample, we consider they are plane wave because the source is far from it. And once it interacts with atoms, with the shell, the scattering wave is spherical, and it has this shape. And the amplitude of the spherical wave is what we call the scattering length. The higher the scattering length, the higher is the amplitude of the scattered wave. So this length is of the order of 10 to the minus 13 centimeters. So it is a short-range interaction. So you will have my slides. So not necessary to write the equation, or so only things that are not described here. So here is a graph where I report variation of the scattering length as function of the atomic number Z. And in blue, you have the different scattering lengths for neutrons. So you see it's a bit erratic. Where in red, you have the one for X-ray. So the X-ray, the one for X-ray is continuously increasing with increasing the Z. So neutron scattering is very important for soft matter because, as you can see, there are huge differences between the scattering lengths of hydrogen and deuterium. The scattering length of hydrogen. So this is important since with polymer system we can label molecules and change the scattering power of the molecule, the scattering length of the molecule, the amplitude of the scattered wave when the radiation fill the deuterium atoms. And okay, so the way we calculate the scattering length of the X-ray, B, is the atomic number times the radius of the electrons. So this, for X-ray, B is increasing monotonously with Z. And it is very weak for hydrogen. So there is the amplitude of the scattered wave, X-ray wave, when they encounter a hydrogen molecule is weak. So now, if you add another atom, so you will have two scattered waves, and this makes interference. So, and there is a phase difference between these two waves, which depend on the delay that the wave reach the second atom. And these are vectors. So the phase difference depends on the vector that between these two atoms, and the difference between the incidence wave vector, Kf, minus the final wave vector, Kf, minus the incident wave vector. And we define another vector, K, Q, which is the difference between Kf and Ke. Q is a scattering vector. And remember, K is a wave vector. So, so when we put a detector after this interference pattern, in fact, we are not able to measure the wave. We measure the square of the scattering amplitude. And we define what we call the differential scattering cross-section, which is the sum over all the atoms, E and G, Bi and Bg, exponential minus E, Q vector, Ri minus Rg. So we sum over all these atoms. You see that the scattering cross-section, there's a product Bi, Bg, which is analogous to a surface. So this is the reason why we call this differential scattering cross-section a section. So the scattering intensity, in fact, is a probability to find an atom BE and an atom BG distance of a vector Ri minus Rg. So for small angle scattering, we consider that there is no change of energy. The modulus of the wave vector incident and is equal to the modulus of the wave vector, final wave vector. We have only a change of direction, which is not always the case for other scattering, neutron scattering, which is not the case for other scattering technique. But for small angle scattering, there is no change of energy, only change of direction. So instead of scattering vector Q, we are using the modulus of the scattering vector Q, but for simplification, we call this Q without any vector and modulus sign. We call this Q. And Q is equal to 4 pi over lambda, sinus theta over 2, which theta is a scattering angle, and lambda is a wavelength of neutrons or X-ray radiation. So Q is a reverse of a length. So Q minus 1 is typical length. So we have to introduce for small angle scattering another notion, the notion of elementary scatter. Before I was discussing about atoms, and now I put some atoms together. For example, it could be H2O molecule or monomer. So, since the size of this elementary scatter is much smaller than the inverse of the Q. Mean that the exponential EQREG is equal to 1. So now the scattering cross section is a product. Is a simple product of a length which is a bit different at the beginning, but this is due to the fact that the elementary scatter is much smaller than the vector Q vector that we will manage. So B is a scattering length of the elementary scatter. So for example, here I took the example of polystyrene monomer, of a solvent, of water, and also of lattice. And so here is a formula, chemical formula of number of carbon, hydrogen, and oxygen. And so B, the scattering length of this elementary scatters, is simply the sum, m times B of carbide, plus n times B of hydrogen, plus P times B of oxygen, and this value of B are tabulated. So if you know what is a monomer, you are able to calculate before experiment what is the scattering length of your elementary scatters. So, but if the more you add atoms in the elementary scatters, you may This is means this is more or less the scattering power, the scattering power of the elementary scatters. Yes, the bigger the scattering power, the more diffusion you will have. If it is small scattering power, you will have less diffusion. The area, it's a bit of area seen by the radiation. So, but if I So now, if I put more atoms in my elementary scatters, I will have a huge B value because I had a lot of B, dependent B. So what is important for the scattering is not B, it's B divided by the volume of the elementary scatters. These are the real power of the diffusion of the elementary scatters. Sorry, yeah. Why the scattering is elastic? No. It's really elastic. No, there are some elastic, but the chain, there are always movement. Elasticity, when you can lose some energy due to the movement of molecule inside the sample. So if the movement of the molecule inside the sample is weak, you will not see difference of energy of outgoing neutrons or X-ray. But okay, yes, yeah. For any case, for both. We don't see. Yes, yeah, yes, because I will come back to what I call the contrast. With X-ray, there is some scattering. There is some scattering density, but we need a contrast with the media. So I will come back later on to this notion. So. So the scattering density is characterizing the diffusion power of elementary scatter. So it has to be divided by its volume. So here I put a table in which you see value for light water, for heavy water, and for polystyrene, hydrogenated monomer of polystyrene, and deuterated monomer of polystyrene. And I compare the scattering density for X-ray and neutrons. And you see, so there is almost no difference for X-ray between H2O and D2O. And also, the scattering length density of polystyrene is not far to the one of H2O. And if I take another solvent for polystyrene, you will have similar values. Now, if you look at the scattering length density of neutrons, for neutrons, okay. Yeah.
Maybe I missed, but why for H2 and D2O, for X-ray it is
The same number of electrons.
And neutron?
So the interaction of neutrons with deuterium is very different. The scattering length is very different. Okay, it's.
What is the interaction with neutrons with the nucleus?
I cannot explain this. We can imagine it at a repulsive interaction, potential interaction. Yes. Blacks. It's difficult for me. I cannot explain this. But you think it is when it is positive, it is attraction. When it is negative, it is repulsive. We are familiar to potential interaction potential, so something like that. So if we look at scattering lengths with neutrons, you see there is a huge difference between the one of H2O and the one of D2O, and also between hydrogenated polystyrene and deuterated monomer of polystyrene. And you see there is a huge difference between the scattering length density of polymer in the solvent. Okay, so polystyrene is not very happy in water, but imagine it will be another solvent. There is huge difference between the scattering length density of polymer and solvent, which is not the case for X-ray. For X-ray, to have some difference, we need to have heavy element inside the monomer. So if you are working with polyelectrolyte, then you will have some heavy element inside the polyelectrolyte. So then you recover some scattering length density, and there are some difference with water. But unless you have heavy element in your monomer, the X-ray is not good. It's better, much better in neutrons. So another principle that I have to introduce. This is true for both radiation, but it's very interesting for neutrons. We'll see later. What is the scattering length density of a mixture of solvents? So in a sample, the mixture of solvent, I take a fraction phi of deuterating solvent and 1 minus phi for hydrogen solvent. Since both solvent has the same molar volume, you can simply add the scattering length density of both solvent weighted by their respective fraction in the sample. So the scattering length density of the mixture is equal to phi, scattering length density of deuterated solvent, plus 1 minus phi, scattering length density of hydrogen. So by this way, by mixture, you are able to vary the scattering length density of a media. Here I take the example of the solvent because it's very easy to understand. So this works this is very useful for neutrons because as I just mentioned before, the scattering length density of H2O and D2O is very different. So by varying the fraction of deuterated water in the media, I can vary the scattering length density of the media in a wide range. Yes. Nuclei may have different isotopes and also different spins, and neutron is measuring this. Is measuring this. So this gives what we call current incurrent signal. It is a flat signal which does not depend on the scattering vector, but it exists. It is a background. The fact that hydrogen, you have isotope and spins in your sample, give a background. So it's not a big problem, but it is a background. But since it is independent of Q, it does not matter much. What will be interesting is what we call the current signal, S of Q, which will give us what are the fluctuations of elementary scatter inside the sample. This is interesting because this is values that this is a parameter that we want to determine to determine what is the structure of the sample. In current signal, there is no specific order, so we will get rid of this by a simple subtraction. But it is a signal that is present. And this signal is mainly due to hydrogen. Hydrogen give a huge incurrent background. So this is a sad news for polymer because polymers are mainly, there are a lot of hydrogen in hydrogenated polymer. So when you use hydrogenated polymer, in addition to the signal which give you information about the structure of your polymer, you will have the background that you have to subtract. So the ratio between the signal that is interesting over the background is less favorable for polymer. Here, but okay, since it is a flat background, you may get rid of it. Oh, this is an ugly slide. So now consider several species, chemical species, with different elementary scatter. So the total scattering cross-section is a very complicated equation. So with neutrons there is an incoherent signal, and the structure factor function which is interesting is we can define several partial structure factor attributed to each elementary scatter. We can separate each elementary scatter. The double sum here can have the double sum over the first species, the second species, and so on. But if you have a lot of chemical species, you have a lot of partial structure factor to solve, and this could be unknown. These are unknown parameters. We can get rid of one using the notion of compressibility, which relate the volume, compressibility, and the fluctuation. The whole volume remain constant. So this helps, so it's a bit complicated, but this helps to simplify the equation and to introduce here the final equation, to introduce a contrast length, K, which is a difference between the scattering length of one element with respect, for example, to the solvent or to the matrix. We choose the solvent of the matrix because it's easy to look at one molecule in the solvent. So we generally the matrix of the solvent is element that is sacrificed by this simplification. So here you see there is you see what is important here, that there is a difference, and the scattering cross section is proportional to this contrast. So you see that you may, in order to have the signal, you have to have a difference, a huge difference. So the scattering length density appear in this equation. It's referred to the question that you asked a few minutes ago. So it's a difference of the scattering power of one elementary scatter with respect to the one of the solvent, for example. Question?
Are we talking about a dilute system?
No, any kind of system. In the partial structure factor, you will have you take into account of the dilute and if it has some concentration. Also, this is a sum. There is a both. Well, there is everything.
So, are we looking at a binary solution here because you want alpha and beta? Are they two species, or what are alpha and beta? Or have I misunderstood? Oh, we've got. So this is a polydispersed system?
It is any system. The sample is full. There is no. There is a solvent, there is a molecule, and the solvent generally is the first species that is remarkable because generally it is a main component. But you fill the space with elementary scatters.
How do you define an elementary scatter?
The elementary scatters is a molecular floater. It could be monomer. It could be a lattice. It is. Yes, because yes, generally yes, because it's a thing that you want to know how they are stacked together or how they are arranged in the sample.
So you consider them all to be the same, and now you're just looking at their relative arrangements in space.
Yes. Yeah. It is also the contrast. But the contrast is almost null in case of X-ray, because if I take because the scattering length density is of water and of polymer is the same. This is a prefactor, and in case of neutrons, it is very weak. In case of X-ray, it's very weak because the scattering length density are almost the same, and in case of neutron, the difference can be much higher. So this is a prefactor of the scattering of the differential scattering cross section. Can you repeat the question?
If the contrast is almost zero in X-ray?
You cannot measure nothing. The contrast is a prefactor of the scattering cross section. So the intensity is a contrast time the scattering function that you want to analyze. But if the contrast is zero, even if there are some organization in the sample, you are not able to measure it. You need to have a contrast between the molecule that you want to know how it is organized with respect to the media to measure something. Even if the molecule has a shape, if you are not able to discriminate, to see it, you will measure nothing. The signal will be zero. But okay, so for the moment, the structure factor, you may have two molecules. So the partial structure factor is composed of contain both signal, the shape of the molecule and the correlation between molecules. There is no assumption at this stage.
So you're not distinguishing between form and structure factor?
For the moment. The beginning, the first equation is no, we don't differentiate between dilute and
why is it like with the Q vector, like for the solid, it's decreasing, like it's equivalently like, so even for like the liquid, after certain length, it starts to decrease, like you have a
yes, this is for solid, these are the structure factor because of the arrangement. So you see peak. For liquids, there are the neighborings, so it gives you oscillation. And for solution, you have generally here decreasing like this.
And why is it decreasing?
Because when you the largest, when you have large signal, large object at small q, you are looking at fluctuation of large object, and they are fluctuate a lot. So the intensity is huge. When you decrease, generally, when you decrease the size, fluctuations are less, so the scattering is less. This is with ants.
To do with the fluctuation around a lattice site, for example, because you can think of it as a convolution in Fourier space. So if you've got a fluctuation of a particle around this lattice site, then you in Fourier space you multiply the lattice by the fluctuation, and and then it tails off. Tails
So you multiply by the number of lattices.
Good.
So
So this was for introduce a contrast. So due to the compressibility, you have M equation, but the total volume should be kept. So by this way we get rid of one component, but this reveal the notion of contrast. To be able to have a signal, since the contrast is a prefactor of this partial structure factor, we need a difference between the species in order to be able to have to measure something.
What is the physical significance of Q here? Does it signify the length of scattering, length scale of scattering?
I don't understand. Yeah.
What is the physical significance of Q here?
Q is a scattering vector.
Does it signify the length scale of scattering?
Yes, inverse. Q is the inverse of the length of observation.
Of the sample.
Of the sample, yes. Small q, since small q means you are looking at large fluctuation, and IQ means you are looking at low scale fluctuation. So the scattering function is a sum. Now you take is a sum of several partial structure factor, and the contrast is a square of the difference of the scattering length density of component I minus component 1, which is generally the solvent or the matrix. So if now you have binary system, so the scattering function has only one unknown function, which is the fluctuation of component number 2, and the prefactor is simply the square of the difference between the scattering length density of number 2 species minus the one of the solvent or of the matrix. So this prefactor of the scattering intensity depend on the radiation. It depends if it is Newton or X-ray, while the scattering function reveal the fluctuation of the nuclei or of the electronic shell of the things, which nearly are close, but there are some difference. So now I consider n identical particle of my bigger n elementary scatters that interact to each other. Means that you are starting to concentrate this object that are interesting for you, and you can separate this in this equation two terms. The one who is dealing with the blue one, who is dealing with fluctuation inside this particle, and which is there, is a number of element of particles times the number of elementary scatter to the square inside this. The form factor, because it will give the shape of this. It will fluctuation of elementary scatters inside this object, plus correlation between the position of this object inside the sample. This is what we call the structure factor. And there are n2 terms like this. There are n terms form factor and n2 terms for the structure factor. So the form factor is inside the form factor and the structure factor. You have to add the form factor and the structure factor. In case of spherical particles, symmetric particle, you can play with the center of mass and realize that this simplifies this big equation with some BI, BJ, exponential EQRG. You could simplify it. And in fact, the scattering function is a product of the form factor times the structure factor. So interparticle, since the center of mass of particle is in the middle of the element, so you can simplify this formula here. So, but for polymer, polymer is not symmetric particle, so you have to add the form factor and the structure factor. Okay. If they are not centrosymmetric. It remains that they are not centrosymmetric.
When you measure Q, you're just measuring the modulus of Q. Aren't you doing an orientational average anyway?
When you measure Q,
If you measure intensity as a function of Q, modulus Q, aren't you doing an orientational average anyway? So you have modulus versus polymers.
yes. Generally, generally the yes, and also a structure factor. I don't know.
It's easy when it's diluted, right? Because then you don't have the correlation.
Yes.
Is the structure factor one everywhere?
Yes.
But then you can compare.
I would say that on average, you have to calculate. It's very difficult, I think, to calculate. All simulation can do the calculation, but there is no structure factor.
In the intramolecular structure factor.
Yes.
Ah, okay, I see. Right, yeah. I'm with you.
So here I took the simple case for the form factor. I took the simple case of a sphere. So in a simple, the sphere is homogeneous. So the scattering length density along the sphere is the same. So the scattering amplitude is the sphere. You take the scattering length density, you go out, and the sum of E puissance EQRG over the volume is also can change E puissance EQRG by sinus QR over QR. So you can integrate over the volume and find the scattering amplitude of a sphere, which has this relation. And the scattering intensity is a square of the scattering amplitude. So by this way, you recover the form factor of a sphere. So the form factor of the sphere is very simple. It depends only on the size, on the radius of the sphere, and it goes to 0 at a very low Q value. Now I speak about the form factor. It is dilute. So generally, when you are looking at dilute solution of something, or dilute things in the matrix, typical small angle spectra are like this. They are decreasing. And we look at different part of this curve to get some interesting parameters. So we look at 0 Q value. Means you are looking far from the object that you want to look at. And this will this will give us something very interesting, which is the number of elementary scatter of the of inside this. We are looking at the Guinea region here, which will give us the mean size of this object. And then when you go at very large Q value here, we are looking at what happens in the interface between the object and the solvent, for example. And in between, in the intermediate range, you will have some decreasing with an exponent alpha. Again, we will have an exponent, which may be characteristic of some peculiar shape. So let's start by small q value. So the scattering intensity is proportional to the volume fraction of the sample. Remember something that you have to have in mind is we want to know what is the distribution, what is the fluctuation of the sample inside inside the sample, and what is important is a volume fraction, not the mass fraction. It is if you want to know how it is organized, people in a room, what is important is its volume, not its weight. So it's a volume times the volume of the volume of the particles that we are looking at, the contrast, and the form factor. So the volume fraction is the number of particles times the volume of particles divided by the total volume of the sample. Since the form factor goes to 1, the scattering intensity at 0 Q value is simply the volume fraction, the contrast that you have calculated before during experiment, because you know what is your sample, you know what is your solvent. So this is a known parameter times the volume of the particles. So the scattering intensity at 0 Q is proportional to this, and generally you know how many particles you put in the sample. You know the volume fraction that you put in the solution. So the only unknown thing is the volume of the particles, which is also related to the molecular weight of the particles. So this, at 0 Q value, you are able to measure the volume of the particles, or the mass, because the volume and the mass are related.
Is it easy to do?
Yes.
Like, you have to calibrate.
Yes. 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 The scattering intensity has to be measured in absolute value, and it's easier with neutron than with X-ray. With neutrons, scattering intensity is in every place in absolute unit. X-ray is a bit more difficult because the flux is too high, and it is saturating the detector. So to measure what is the flux, the incident flux, we need to attenuate the beam or to use another detector which is not sensitive, not as sensitive as the detector to record the scattering intensity. But then we have to calibrate this extra detector. With X-ray, it's a bit more difficult, but it is possible. With neutron, it's much more easy, so it's done. So we know everything. If we know the scattering intensity per unit volume in absolute unit, you will be able to measure the molecular weight. Better sometimes at GPC if it is not well calibrated. If you have calibrated with polystyrene standards and the polymer is not polystyrene, you may have some trouble. Okay, so then the Guinea regime. So Guinea regime. So the form factor of the molecule is this equation, and this equation can be developed at 0 Q value using Taylor expansion and so on. And whatever the shape of your object that you want to know the size and the shape, you can always develop this formula, and it gives this equation. Whatever the form, the only condition is to be at low Q value, because you can develop this equation at low Q. And this is a Guinea approximation. The form factor is equal to 1 minus Q square Rg square. Rg is the radius observation, the mean radius of your object divided by 3. So from looking at what happens here, when you start to go down, when the structure factor is when you enter this regime, you will be able to measure mean size of the particles. So what is the radius observation? So the radius observation is this equation. So the scattering length density R square divided by variation of the scattering length density inside the particles. So it's like a moment of inertia that you learn at school. So for the sphere, the volume is this. So Rg is a sum of R4 over R2. You can play, and you find that Rg square is equal to 3 divided by 5 times the radius of the sphere. For a vesicle, the vesicle is have a thin layer here. There are an inner radius and an outer radius. So you can play again this integral and find that the radius observation depends on the external radius minus inner radius, etc. And in case of very thin vesicle, the radius, because all the material is here at the radius of the coquille, of the shell. So Rg is equal to R. So by measuring the radius observation, you may access to the size depending on your system. So how to measure the radius observation? So P of Q can also be expressed as exponential minus Q square Rg square divided by Q. So you can plot log the intensity versus Q square. This will give you a straight line, and Rg square is 3 times the slope of this line. This is how to measure the radius variation. There is another approximation of the form factor. The form factor can be also derived this way. And now we use what we call the ZIM representation, that is the inverse of the scattering intensity versus Q square. It's also a straight line. And the radius observation is equal to 3 times the slope divided by the intercept. And this ZIM representation is good for polymer because it deviates from the slope, from the straight line at higher Q value than the Guinea approximation. Remember, the radius variation has to be measured in Q Rg smaller than 1. So after this, it's no more linear.
How do you find this value of 1 over Rg?
1 over Rg.
So when you look at the plot,
Yes.
where do you look?
I look to measure Rg. I look at this part when it starts to deviate from 1, when it's decreasing here. This is region where QRG start to start to move, to change linearly with Q square. And depending on the shape of the scattering intensity, this will be a straight line longer, at larger Q value. You can go to QRG about 2 sometime in some case. But the closest QRG smaller than 1, the better the accuracy of your measurement. Now I go to the Perot regime. At large Q value, we are looking at the interface. And at this scale, all the objects that we are looking at appears flat. And in fact, the scattering by flat surface is fractal because if you consider a disk, if you are looking at a big disk, you find it is a disk. If you go closer, and it's always a disk, so it's a fractal. Okay, but for the Perot's law, decreasing is Q minus 4. This is what we call the Perot's law. Its characteristics of abrupt interface, and then the limit of scattering intensity at low Q varies at the inverse of Q to the power 4, and the prefactor is 2 pi, the contrast, times the total interface in the sample, specific area in the sample, the total number of surface inside the whole volume of the sample. So how to measure this specific area? So since the scattering intensity is decreasing as Q power 4, we plot Q4 times the scattering intensity versus Q. And at a given moment, it is flat. And the specific area is this value. So this specific area does not depend on the geometry of the sample. And you may have some deviation to this Perot law if the surface is rough, or if close to the surface, the scattering length density of the material is changing a bit. Sometimes it's more dilute, or so you may have some deviation to the scattering, to the Perot's law, due to the roughness of your material, or to some variation of the scattering length density when you approach the surface. I have to say that this Perot law is observed for sphere, for colored particles. It is almost never observed for polymer. So. I get only for the moment the specific area of the sample. These are known value. This 2 pi is 2 pi. So the total surface of interface in my sample, and now I enter the detail. So assume that my particle is a sphere. So the surface is a number of particles times the surface of one sphere. The total volume is this relation. So this simplifies, and finally we get R, the radius of the sphere.
So it's the distance at which you start to see a flat interface.
Yes. This is R is the size of the sphere.
That's what you're getting from Q, right?
Yes. This we measure S over V. V is the total volume of the sample. We measure the number of we are measuring the number total number of interface inside the sample, and to access to have better things. we have to make some assumption here. In the case of sphere, it's very simple. So this could be interesting for soft matter. For large particles, sometimes it's not possible to access very low Q value and to access the Guigné regime because we are limited by the machine, by the technique, and we are not able to reach the Guigné regime, which is QRG much smaller than 1. But if you are lucky, you will have a plateau, and the plateau will give you a mean size of the object. So you can use this to have the mean size of your object, even if you... okay. No, it's a radius of the sphere. Yes, yes. So the total area of is n times the number of sphere times the surface of the sphere. R is the radius of the sphere. Yes. Yeah. 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 Yes. We can check if it is sphere or not. if the both does not coincide, means that it is probably not a sphere. And then there is the intermediate regime. So this is an exponent which generally characterizes the shape of the object. And then I come to the case of fractal object that you have seen a couple of times. So whatever the scale of observation in between the whole size of the molecules and the elementary size of the structure, it looks the same. The structure looks the same, and you have a dependence of the mass, which is also the number of elementary scatter. It increases with the object size. It follows this law, where df is a fractal dimension of the object. And what we are measuring in Newton scattering is a pair distribution function, which is a probability of number of molecules of air divided by the volume, r to the power d. D is the dimension of the space. Generally, I prefer d equal to 3. But and so the scattering intensity is the Fourier transform of G de R. So the scattering intensity decrease Q to the power minus df. df is a fractal dimension. So in the intermediate Q range, if you plot log de E versus log de Q, you will have a straight line, and the slope of the straight line is a fractal dimension. So fractal particle, you have seen some, a lot, in fact. You have seen the Gaussian chain, a chain in a good solvent. The fractal dimension is a Gaussian chain is 2, and the mass varies as r square. The Napoleon law is r varies as m à la power 1/2. So in the intermediate scattering vector, the scattering intensity will decrease as Q minus 2. In case of the good solvent, the fractal dimension is 5/3, and the decreasing of scattering intensity will be Q minus this fractal dimension. For a rod is also a fractal object. If looking, this is a rod. If you look at this side, it's a rod. If you look at this side, it's a rod. So the molecular weight of the rod varies as the length of the rod. The fractal dimension of a rod is 1. So you will see Q minus 1 dependence of the scattering intensity, mean that the molecule that you are looking at is elongated, looks like a rod. For a disk, it is the same. The disk, the fractal dimension of a disk is 2, and you will see Q dependence, Q minus 2 dependence. So here you see, for a polymer, you may have Q minus 2. For a disk, you may have Q minus 2 also, so could be a problem. But generally, people know that they put polymer in the in the sample. So, so fractal in the intermediate Q range, the form factor of a disk has this equation, and here are the log-log plot of the intensity versus Q, and you see for polymer, for disk, and here is for finite of a rod. We will see there are some oscillation, but there are huge space where the variation has a fractal dependence.
What are the oscillations at IQ?
At IQ, we are looking at the diameter. For example, we don't see anymore this length. We are looking at here, and these are oscillations because we will see the radius of the rod. I will show an example with a sphere and with a vesicle that we will see. Now I speak about the intermediate range for the fractal. But this is important for polymers because some polymers are elongated, and you will encounter a Q minus low dependence of the scattering intensity. This will indicate you that the molecules are very elongated. So I give this example here. Okay, so we have calculate the form factor of a sphere. We can calculate the form factor of an empty sphere, a shell here. It's a sinus QR sur QR. Okay, and for example, the case of the sphere. Now I plot the whole form factor of a sphere. It has this expression. You have this representation, form factor versus Q. And you see there are plenty of oscillation. So here is a radius observation. And here the scattering intensity of the form factor goes to zero at accurate position of Q. The first oscillation appears at Q 4.5, and the second oscillation, etc. You can calculate from this equation at which QR value, you have to go to 0. And also, a characteristic of sphere is that they have sharp interface, and the envelope of the decreasing is Q minus 4 because the sphere has rough interface. In fact, we never observe the oscillation like this for different reasons. The first reason is the sphere can be, the sphere that we put in the sample can be polydispersed. So the value of QR at which it goes to 0 varies because there are different air in the solution, in the sample. The other reason why we never observe so many oscillations is due to the instrument. We never sent very small beam on the sample because we need some flux. So the beam as the neutron beam or the X-ray beam has some size. So the Q value is not well defined due to the size of the beam. So Q is varying a little also. Also, another reason for which we don't have Q value may vary is the wavelength. The wavelength that you are using is not perfect. It could be a broad wavelength. We can have a wavelength plus minus 10% or 5%. So this will give you uncertainty of Q value. So this will spread a bit but the instrumental resolution, we know, because you know what is the distribution of the wavelengths of neutrons, or what is the distribution of the wavelengths of X-ray, which is very narrow for X-ray, but with neutron it's not so narrow. We know the size of the beam. So we are able to, we know exactly what is the resolution. The only parameter that we don't know is the polydispersity of the sample. Yeah.
Can you remind me what's the second minimum corresponding to here?
The minimum, say, if you go well, look, calculate when this form factor goes to 0, you will find, because there are sinus and cosinus, and you will find this value. These are because the variation of the form factor here, the form factor there are sine and cosine value, and sometimes it goes to 0. P de Q is 0. So you can calculate very easily at which QR value this function goes to 0. And as it is sine and cosine, there are several values of QR for which the scattering intensity, if the form factors goes to 0. So anyway, generally we have things like that. You have some oscillation. We have some here. The first oscillation. Normally, the first oscillation is at this value. We may have the second one, but here it's a bit difficult to determine exactly what is the minimum of the scattering function. And in order to enhance this, we plot. Oh, sorry. So here is an example of a silica particle of different size, and from the position of this oscillation, you know exactly that, for example, here the oscillation is at this Q value. The oscillation of the second sample is at lower Q value. Remember, Q is the inverse of the size, means that the radius of this sample is larger than the radius of this sample. By simply looking at the curve, you have this information. Also, the intensity. I mentioned that the scattering intensity at 0 Q is proportional to the volume of the particles. So here, since the radius is larger, the volume is larger, so the intensity is higher than here for the. So, okay. So on this curve, so if I plot logarithm of intensity versus Q square, it is a straight line, and the slope gives me the radius of gyration. And if I assume that it is a sphere, it gives me the radius of the sphere. Now, I told you that it is rather difficult to see what is the minimum of intensity here, but a better representation, you plot Q to the power 4 times the scattering intensity, and now this change of slope is much better. We can see much better now, and the minimum Q value is this value. So you may have a better simulation, a better value of QR by this, simply by changing the representation, not changing the intensity, it's changing only the representation. Okay, and that. Okay, so and also the Paul's law here, the flat signal gives us 3 divided by r. R is the radius of the sphere. So you have plenty method to access the parameter, but here there is only one parameter, which is the radius of the sphere. Here is a form factor of a vesicle. A vesicle is simply 2 spheres, one in another one. And we can calculate the form factor. It's time?
12:15.
Okay. Okay. So the typical characteristic of a vesicle is the intermediate region. When we look here, when you are here, the large vesicle appears as a flat, appears as a disk, and the characteristic dependence of a disk is a Q minus 2, remember? The disk is a fractal, and here, when you will have a Q minus 2 dependence, you can suspect that you will have a vesicle. Vesicle is often encountered in a block copolymer. When you put in amphiphilic block copolymer, when you put in water, there are the hydrophobic molecule polymer goes inside the layer. If it is rigid, also, and okay, you may encounter vesicle in block copolymer. And if you got such a Q-2 slope, means probably you may have vesicle in your sample. Remember here, here for sphere, it is Q-4. So the presence of Q-2 you can suspect presence of a vesicle. So here we play the same game, the radius of gyration, this the size, the mean size of the mean radius of the vesicle, and at large Q here we are looking close to the membrane, and this big expression derived like this, where E is the thickness of the membrane, and if you plot logarithm of Q square times intensity, in the intermediate regime the scattering function is like this. If you plot logarithm of Q2 to the power 2 times the scattering intensity versus Q square, you have a slope, and the slope gives you directly the thickness of the membrane. And if you are lucky, you will see a nice oscillation also, which is due to the membrane thickness. So here I show you simple case of sphere, of a vesicle, but there are many form factors that have been calculated. There are two open source software that you can use. The one is SASFIT from PSI in Switzerland, and the second one is SASView from United States. It's open, everybody can use it, and there are plenty of size, of shape. There are plenty of shapes that I've been introduced in this software, and by fitting your data with this different form factor, you may have the different parameter of your system. You have to introduce also the resolution, but this program allow you to introduce the resolution of the machine. Generally, the data that you have, there are 3 columns. The first column is the Q, the second column is the scattering intensity, the third column is the error bar and the scattering intensity, because you need, and the third column is the error bar on Q, because we need intensity, so it depends on the wavelength distribution and the size of the geometry of the beam, and you fit your curve with this form factor.